All right, next section we have is 6.3 Volumes of Revolution. This section is actually quite commonly covered in a high school calculus curriculum, especially if you took AP or BC calculus. This is fairly common. It's a really intuitive section, I would say, at least visually, to understand what's happening. These problems can still be difficult to compute. The geometries can be complicated for some problems, but generally speaking, I think once most people have a good mental understanding of what's happening. In other words, how we would rotate something in order to create an image or a shape in 3D. If as long as you really understand that, you can rely on that intuition and understanding to carry you pretty far through this section. So some of you may very well know this material if you've taken calculus in high school. If you haven't, well, here it is. So for volumes of revolution, the idea is that we can take an area in the xy plane, such as this triangle, and we can imagine rotating it about an axis, such as the y-axis. So you can actually construct this. You could take like a wooden dowel or some sort of rod, and then you could take like a piece of cardboard, tape it, cut it out so it's a triangle, tape the edge of it, this edge here, tape it to the rod, and then if you place your hands here or here on the end of the rod, and then you spin it between your hands really rapidly, sort of like what you can do with a pencil, if you do that and you look at it, or have somebody else do it and you look at it from a few feet away, you would see a cone. So we are really just imagine spinning this out. So this would come out of the page and into the page. Okay? What happens if the area we rotate is a semicircle? So if we take this area and we rotate it this time about the x-axis, we would see a sphere. There are a couple different ways to generate these shapes, or at least different mathematically different ways to compute the volume. Conceptually, we are still rotating something about an axis, but this volumes of revolution section is really broken up into two main sections. 6.3, where we investigate the disk or washer method, and then 6.4, which is where we talk about the shell method. In both cases, in both sections, we are rotating an area in 2 dimensions. So, sorry, let me rephrase that. We take an area in 2 dimensions and we think about rotating it in through the third dimension. For instance, this triangle is written or drawn in the screen or in the paper, and then we would rotate it coming out of the screen and going into the screen like that. What's different between the two sections is how we will compute the volume. Okay, so here we are going to detail the disk washer. The disk method, I should say, which is the same thing as the washer method, except for really a washer is equal to disk 1 minus disk 2. So we'll come back and talk about this later in the section, but really you will hear me say disk method, you'll hear me say washer method, but more commonly than not, even if I'm talking about a washer, I may still use the word disk, because really a washer, as we'll find out in a few videos later on in the section, that's really just the difference in two disks. Okay, so let's say we've got a function and we want to take the area between the x-axis and the graph of f, between, let's say, x equals a and x equals b, and this area in the xy plane, we're going to rotate it about the x-axis. Well, one way we can do it is by just thinking about a representative little piece. So let's just say we're at some arbitrary x value. We're at some x value x, and then imagine this being rotated, just this one line segment. Well, if we rotate this line segment, this is going to trace out a circle. It's going to trace out a circle. That's exactly what this circle here is. And furthermore, what this tells us actually is that this distance right here, the length of this line segment, is the radius of this circle that's being traced. And a quick little comment on jargon. If you have a circle is just this actual curve that I drew. Just the curve. It's not the points within. It's just the outside. When we say the word disk, we are actually referring to not only the circle, but also all the points that are contained within the circle. So a disk is really a filled-in circle. Okay? So I can also say that this length is the radius of the disk. Okay? So, essentially, what we've already done in section 6.2 when we talked about finding volume, if we know the area of the cross-section, then we can find the volume by integrating that cross-sectional area. So what we just did here was we went ahead and considered some intermediate slice somewhere between A and B, so a representative slice, and we can imagine or conceptualize this rotating out and tracing out a circle. Then the area contained by that circle is exactly the cross-sectional area. And we can continue doing this for a bunch of different circles. So for instance, that's what is drawn over here. We can think about just drawing a bunch of circles. They get wide, they get bigger as you go. So if we know the area here, so let's see actually, what is the radius specifically? Well, the radius specifically is just the value that you get. It's this distance here, which is a y value. So the radius in this case is y, and because we know this function, we know that the y value is given by f of x. So the area of such a representative circle is pi times the radius, which is the function value, squared. That's exactly what we have here. So if we want to figure out the volume of such a thing, we would take our cross-sectional area and integrate it. So the constant was moved outside, but the area is pi times the radius squared, and we'd integrate from start to finish. A quick comment here that I think is really, really, really important when you're first learning these, or when you're first learning to do these kinds of problems, there's a tendency for textbooks, and if you just, for instance, if you were to search for the volume of revolution disk method formula, for instance, it's very common for you to come up with this formula. And that's excellent, that's great, it's true, but it's not true in general. It depends on exactly the geometry. So for instance, in the previous problem, not problem, but the previous page, we were rotating about the x-axis. Not only were we rotating about the x-axis, but the area that we were rotating actually touched the x-axis. So the region that we were rotating, that region touches our axis of rotation. So there's a couple of things that can happen. Well, for instance, one thing is perhaps instead we just rotated maybe this region. Maybe we didn't go all the way down. We just rotated this region. Well, in which case, we're still rotating about the x-axis, but there's this gap here. There's this gap. So what this would actually look like is, if we were to rotate it, the image would look something like this. So we'd have this outer circle, and we'd have this inner circle. So this inner region here, that's hollow. What's really solid here is this. That's solid. And this is precisely what a washer is. It's a big disk, outer disk, minus inner disk. You first find the volume of just this, then you subtract the volume of that. So a washer is big disk minus little disk. In which case, this formula here is not valid. Another way that this formula may not be valid is if you are rotating about a shifted axis. So instead of rotating about the x-axis, what if you were to rotate about the axis y equals negative 12? In these cases, this general formula doesn't hold true. So what's really important here is I'm going to write down that this formula here, this one right here specifically, only applies if rotating about the x-axis and the region of integrate and the the region that you're rotating touches the axis of rotation. If it doesn't, then this formula here is a little bit different. Same thing goes for this half here. But instead of the x-axis, it would be the y-axis instead of this x-axis here. So there's a lot of differences, so you got to be careful. Okay, we will start our next video with example 1.